Well, good morning, guys. You may not be watching this in the morning, but I am making it in the morning, so I'm going to stay with that. And it's a little bit more like our regular class. Today, we're going to talk about what we call limiting reactants. And the discussion prompt that I had you do last week about the recipe adjustments started to prepare you for this. I'm also posting a link to a couple videos that actually explain limiting reactants on the content page. So maybe you watch those first, maybe you do the note first. That's totally up to you. But what are limiting reactants? You will see the term interchangeably with limiting reagent. I even switch back and forth between those terms, so just recognize both. We need to understand that chemical reactions are occurring in defined proportions, right? So we know we should be very comfortable now with mole to mole ratios, or recognize that, for example, in the reaction of hydrogen gas and oxygen gas that forms water vapor, let me just balance this out right now, we see that 2 moles of hydrogen gas react with 1 mole of oxygen gas to make 2 moles of water vapor. Or 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 1 molecule or 2 molecules of water. However, if one of the reactants is in a limiting amount, so doesn't match the actual amount required based on the other reactant, we're going to see less product formed. Now, it's not possible to have half of a molecule of oxygen. So we're not going to talk too much about molecules, because also the chance of a reaction happening with a single molecule and not like billions of other molecules of that same element around or same compound around is very, very, very unlikely. So if we looked at moles here, well, if I needed 2 moles of hydrogen and 1 mole of oxygen. If I didn't have 2 moles of hydrogen, then the amount of oxygen used would also decrease and the amount of water used or produced would decrease, right? Let's take a look at this is a chemical reaction, okay, but we'll put a little bit more in household terms. So I've been making bath bombs over this shutdown time. 1, because I refuse to keep paying $5 to $7 for a single bath bomb, and 2, I am bored. I am very, very bored. So to make a bath bomb, the standard recipe would be 1 cup baking soda, ½ cup citric acid, ¼ cup sea salt, ¼ cup cornstarch, and 3 teaspoons of essential oil. And this would yield, okay, yield means produce, 5 bath bombs. I am not just going to use the word bombs. But we all know that we are running out of supplies, and it's not just pop to the grocery store. So maybe one day I'm working, but I only have a ½ cup of baking soda left. So that's going to adjust the rest of the amounts that are used of the other ingredients, right? If this is decreased by 50%, well, so will the citric acid. So that would become a ¼ cup of citric acid is required, 1/8 of a cup of sea salt, 1/8 of a cup of cornstarch, and 1½ teaspoons of essential oil. That's also going to change the yield, right? So the yield is now going to be half of that, and it will give me 2½ bath bombs. Now in this situation, the baking soda was the limiting reactant or ingredient, because that's the one I didn't have enough of. All the rest, we had what we call excess. So if this was a chemical reaction and I still mixed all of these in with my limited amount of baking soda, these are the proportions that would be used in the chemical reaction. Now, when we cook, when we bake, we know that it doesn't work the same. We don't just add our regular amounts in and only a proportion will be used. But we're going to move on to actual chemistry now. So, to determine what the limiting reactant is in a chemical equation, we're going to use, you got it, stoichiometry. And we're actually going to look at how much product would hypothetically be produced by each of the reactants. So just a little clue. How do we know that it's a limiting reactant problem? We're going to be given amounts of all reactants. They're not referred to as excess. So typically I'll give you a specific mass of both or all three reactants, or a mass or a amount of moles. If it's a single reactant in a decomposition reaction, well, there can't be a limiting reactant because there's only one. Let's try the problem out, shall we? Yes, yes we shall. I know this reaction comes up a lot, nitrogen and hydrogen gas forming ammonia, but you know what? It's a simple one. So our question is, if 4.20 grams of nitrogen reacts with 0.750 grams of hydrogen, how much ammonia will be made? And right off the bat, I notice I'm given the mass of both of my reactants, so one of them will be limiting. Okay, step one, as always, write that chemical equation and make sure it's balanced. That's going to be nitrogen gas plus hydrogen gas forms ammonia gas. Take a moment and balance it, like so. Now we're going to go into our regular stoichiometry of it all. I'm going to keep the steps over on the side here. So I'm going to make my trusty chart. This is how I've been doing it since I took grade 11 chemistry. So step 2, find the number of moles of the reactants. So I'm going to start with my mole to mole ratio, which is 1 to 3 to 2. I've been given the mass of each reactant. I have 4.20 grams of nitrogen and 0.750 grams of hydrogen. Let's find the number of moles. Remember that number of moles is mass divided by molar mass. So I'm going to work through these. You guys should pause and find the number of moles yourself. Okay, with sig digs, I find the number of moles of nitrogen gas gives me 0.150 moles. And I have 0.371 moles of hydrogen gas. So that's step 2. Step 3. I'm going to find the N of product based on each reactant. So I'm going to use mole to mole ratios for my number of moles of nitrogen to see how much ammonia it would produce, and my number of moles of hydrogen to see how much ammonia would produce. What I can't do, and what a very common and easy instinctual mistake to make, is to say, oh, well, there's fewer moles of nitrogen, so that must be the limiting reactant. We need to compare to our mole to mole ratios. All right? So the option I'm going through right now is showing how much product it would produce. I'll show you another comparison you can make as well after. So our mole to mole ratio for nitrogen to ammonia is 1 to 2. So that means we're going to end up with 0.300 moles of ammonia. Our ratio of hydrogen to ammonia is 3 to 2. So that would be 0.371 mole to X. And that would give us 0.2475 moles. So these are potential amounts of products. Okay, we can see right here, this is the smaller amount of product. So that means that hydrogen is the limiting reactant. So any calculations we do for a limiting reactant problem, we have to use the amount of the limiting reactant. There is more than enough nitrogen gas present. It will not all be used. So we have to use this value, our limiting reactant, to predict the amount of product. Now the question actually asked how much ammonia will be made. So I'm going to take this amount and turn it into a mass. Mass is moles times molar mass. So that's I need some state there, 0.248 moles times, let's do smaller math quick, 14.01 plus 3 times 1.01, 17.04 grams per mole, and that gives us 4.23 grams. All right, so my final answer would be therefore 4.23 grams of ammonia will be produced. So what is the other option for how to compare? The other option I could do is I could just say, well, let's compare my reactant values using the mole to mole ratio. So I could say right here, my ratio of nitrogen to hydrogen needs to be 1 to 3. So if I have 0.150 moles of hydrogen, how many moles of nitrogen, or if I have 0.150 moles of nitrogen, how many moles of hydrogen do I need? Well, that would give us X equals 0.450. I don't have 0.450 moles of hydrogen. I have less, so therefore, H2 is limited. All right. Now, I like the product method because it does part of the work for me. Unless I've been asked how much mass of product, so by figuring out the moles of product, well, I'm already partway there. But this is an option as well. Let's do one more sample problem. Okay, I'm asking you to determine the limiting reactant when 1 gram of calcium fluoride reacts with 15.5 grams of sulfuric acid. Take a moment, see what you can do with this chemical equation. This is part that we had to drop from the course, unfortunately, in our 2-week shutdown, but your grade 10 knowledge should let you do this, because as you write it out, we'll see calcium fluoride, which PS is a solid. You know how to write the formula for sulfuric acid, and it's aqueous. This is a double displacement reaction. So what does it form? Figure that out. Press pause. Okay, double displacement. I know that the cations switch places, So I'll have a compound that's hydrogen and fluorine, and I'll also have a compound that's calcium and sulfate. Calcium sulfate is a solid. We are going to learn how to predict whether it's solid or liquid in our next unit in May, which is startlingly close. And then we have hydrofluoric acid. And then we need to go through and balance it, which is done like so. Okay, so start with your chart. Our mole to mole ratio, 1, 1, 1, and 2. You know what I really like? A nice 1-to-1 mole to mole ratio, because then it's very easy to compare the number of moles. So what's the mass given of each product? We have 1.00 grams of calcium fluoride and 15.5 grams of sulfuric acid. We can't directly compare masses, so let's compare number of moles. Okay, so I find in my calculations that I have 0.0128 moles of calcium fluoride, and I have 0.158 moles of sulfuric acid. Now, all I need to know right now is what the limiting reactant is. So I could use the method on the previous page where I used mole to mole ratios to find out the amount of one of the products. But I'm also going to recognize, hey, these have a 1-to-1 mole to mole ratio. So if I have 0.0128 moles of calcium fluoride, well, that would require 0.0128 moles of sulfuric acid. I have much, much more than that, like 10 times as much of that. So which reactant is limiting then? If I have more than I need here, that's right. Oh, my 8's missing. Okay. This is my limiting reactant. So I'd say, therefore, calcium fluoride is the limiting reactant. And that's that. That is the end of our lesson today, guys. The only new piece is that there's limiting reactants. All the rest of stoichiometry, you need to be practicing. I know you're not necessarily uploading every full question to me online, but practice the full format. Please, please, please. It'll help you so much in the long run. And then as we move forward, you're going to see this in the rest of the course. All right, stoichiometry does not go away. It is the foundation of grade 11 chemistry. So take a look at the rest of the assignments for the week. I'm still adjusting exactly what we're going to do as I write this, so I don't have it off the top of my head, but I am going to have a lab simulation for you to do. Make sure you touch base if you have any questions. Have a great day.